Hi, everybody. I'm Tanner. I'm one of the Vivian students, and I'm going to tell you about a work that we published almost exactly 1 year ago today. CiMLoop, a flexible, accurate, and fast compute and memory modeling tool. This was published at ISPASS 2024, and we actually got the best paper award for it. Before I tell you about our tool, what is compute memory? So, why would you do compute memory? We use compute memory often to accelerate deep neural networks, whose operations often consist of large matrix vector multiplications. So as seen here, you have a green weight matrix multiplied by a blue input vector to get a red output vector. When you execute this in hardware, you'll often have a memory and a compute. You'll store your weight matrix in your compute. You'll store weight matrix in your memory. You'll fetch that to your compute, multiply it with the input vector, and get your output vector. There's a problem with this approach, however, and the problem is that you spend significant energy moving DNA weights from memory. This has actually been getting worse with modern LLMs, which are often doing many, many generations of tokens, and each generation they have to fetch their entire big weight tensor. So this is a growing problem as deep neural networks are getting bigger and more memory intensive. So one way to address this problem is to, instead of moving your weights from your memory to your compute, let's just do the compute inside the memory with compute memory. To do that, we'll have our weights stored directly in the memory array. One approach to do this is analog. There are also digital approaches, but we'll focus on analog for this presentation. When you do it in analog, you'll apply your input vectors, those 1, 2, 3 values over on the left, to the rows of the memory array. And you'll do your computation in the memory array, and you'll get your outputs out the bottom. Now, this isn't the full picture because, of course, if you're doing your computation in analog, the rest of your chip is digital, you need some kind of interface circuits. So for this, we'll need a digital analog converter, or DAC, on the left, and an analog digital converter, ADC, on the bottom. There are two advantages to this approach. The first one is that you do not spend any energy moving your DNN weights. They just sit right there in your memory array the whole time. The next advantage is that your memory arrays are very large and they can run many operations in parallel. Think about all the gigabytes of DRAM that you have on your chip or next to your chip, all operating in parallel, different multiply accumulates. That's kind of parallelism that compute memory might be able to provide. So this is an exciting topic. And because it's an exciting topic, there are many people researching it and many different opportunities to optimize it. There are people researching devices, which are the pieces that store your weights and perform computations in your array. There's your circuits, such as the ADC, the DAC, and other things that do on-chip actions and data movement. There's your architecture, which is what components you use, how many, how do you tie them all together. Your workload, what DNN you're running. And finally, your mapping, or how do you actually put your DNN into your chip. There's opportunities in exploring all of these levels of the stack, but there's also problems in exploring all levels of the stack. And to illustrate these problems, I'd like to ask you to put on your architect's hat and compare a couple of architectures for me. So we've read 3 papers from JSSCC and VLSI in the past couple of years. They're all very exciting. They promise big benefits if you run their compute memory algorithms. We'd like to find the most energy efficient architecture of the 3. However, when we compare them, we have some problems. The different results will have different technology nodes, different devices, workloads, supported resolutions, and we actually can't compare any of them. The reason we can't compare them is that all the levels are interacting with one another. We can't look at any individual design decision because all of the published results that are out there will be changing all of these different variables. So how do we make any decisions if we can't compare them? To do this, we'll use a modeling framework. So we'll build the modeling framework, CiMLoop, that will take in, over on the left, your workload, architecture, circuits, and devices in those 2 boxes over there. On the right, we'll perform a mapping search. This one will generate different mappings. It will apply those mappings to the workload and architecture, send that to a full stack model to get our energy and area, and then it'll pick the best mapping and finally give us the system, energy, area, and throughput given all of our design decisions. In order to build such a modeling framework, we had to address a few challenges. The first one is that we have to represent the co-design space. The challenge here is that there are diverse choices at each level, so we use flexible, user-defined specifications for every single one of these levels of the stack in order to let users effectively explore and model them. Next, we'd like to accurately model energy. The challenge here is that workload values and architecture representations will affect circuit energy. When working in the analog domain, these voltages, currents will all interact with the different design decisions you're making, and this will result in some pretty difficult to model challenges. As a solution, we use energy models that will capture these cross-stack interactions in order to accurately capture the trade-offs. Finally, we'd like to quickly explore the large co-design space. Problem is, deep neural networks are big, and in order to accurately model the energy, some prior works have modeled many different values moving through the DNN. We're talking millions, billions, trillions, and this is slow. So as a solution, we'll use statistical energy models that are more than 1,000 times faster than prior accurate models. Let's get started. We'll dive into number 1, represent the co-design space. We'd like to represent a wide variety of different designs out there. And the first challenge is that all of these designs are going to use different components. And how do we actually model all of these? For the solution, while it wasn't easy, it is pretty simple. We'll use a library of circuit and device models, which include many of the ones out there, allowing users to plug and play with whatever they would like to pick from published literature. And we'll also include a plugin interface that lets users apply or create new models in order to build their own designs from scratch. A more nuanced question is, given components, how do we actually connect them in order to create a full architecture? Your system is going to be made of a variety of different components, and data is going to move through it in different ways. There are some ways that it's valid and some ways that it's invalid in which data can move. So we want to represent how these components connect and move data. But why are we actually moving data in the first place? What makes a good or bad way that we move data? So one good way we can move data is in a way that exploits reuse. So this blue path up at the top is a good path for inputs. It starts in your backing storage right here over on the left. It travels through the digital analog converter, and then it visits 3 different memory cells. And we'll say that each of these memory cells will perform one computation with the input. The cost, of course, is that you start in the backing storage and you move through the digital analog converter. So you paid for one storage read, you paid for one DAC convert, costing energy. But the benefit is that you got 3 times memory cell computations with this one input. So the nice thing about this path, actually, let's start with an output path. So similarly for output paths, we can say that one output might start with this memory cell. It travels through 2 different memory cells, and if we're operating the analog domain, this output might be an analog current that gets added across the 3 cells. So we get 3 memory cells computing with one output, and then traveling through the analog digital converter and move to the backing storage. So just like with the inputs, we got the benefit of 3 different computations for one output, but we paid the cost of 1 convert with our ADC and 1 storage array. So 3 times benefit, 1 times cost. Where do these benefit and costs actually come from? Well, it's reuse. When we reuse one value across multiple parallel components, we get more bang for our buck. Here we'll use spatial reuse, where one value is used across multiple different memory cells, performing multiple different computations, ultimately for only 1 storage read. So more bang for our buck, or more computations for our ADC, DAC convert, and memory access. Similarly to spatial reuse, we also have temporal reuse. Here we have one weight being stored in a memory cell. So we'll look at this top right memory cell. We keep the weight in there for some number of time steps. As n grows very large, we're just keeping the weight in the memory, not moving at all. The cost is 1 storage array. So if we compute each time step, we get n computations for only 1 weight. So the nice thing here is that we explore temporal loops. Again, we get more bang for our buck, or more computations for our initial weight rate. So now that we understand both reuse and how components might actually connect together, we can define our system. So we start with our circuits and devices, or our components, and we define how they connect together with permitted reuse patterns. And now we define our system. But you don't have to take my word for it, because we actually provide models that you can look at that show that this is sufficient to accurately model a wide variety of works out there. So right now we have open source models of 6 different works. The library of open source works has actually been expanding, so it might be more than 6 at the moment. But this is effective for representing a wide variety of different designs. So we integrate this in the modeling framework. Over on the left, that red arrow points to the component model library where you integrate your user-defined components. Then on the right, we have a flexible full stack model that includes how the components connect together and performs a mapping search. So this is nice. We can represent a lot of different architectures, but there's also a problem. And the problem is that prior works that look like this can have very high error. In fact, prior modeling works may average 28% or up to 70% error in their energy estimations. The reason why is data value dependence. So as an example here, I have two different devices in your bottom right. One common device that's used in compute memory is a resistive device, where your weight is programmed in as a conductance in the device. Then we'll read our value from the device using a voltage. So on the right device, I have a value of 3, representing a weight value of 3. And on the left device is a value of 3. The right device is a value of 1. And they're represented with conductances of 3 and 1 microsieverns, respectively. If we read these with the same read pulse, we'll get a factor of 3 energy difference between these two devices. And this problem can actually become very salient with full-scale energy estimations. When you have a large array with many different weight values and many different input values being propagated around, the actual weight and input values being stored can significantly impact your overall energy. So we need to capture this data value dependence in order to be accurate. In order to accurately model data value dependence, we will answer a few questions. The first one is, what DNN value are we processing? What value, here, it'll be one from the weights, is being programmed into these devices. Next, how is the system going to represent these values? DNNs and systems don't actually look at values, they look at the bits and values. So when we look at this in a system, we'll need to encode this value as the bits in the value. And finally, to where do we map the bits in this value? If we support 2 bits in each of our devices, we might take the first 2 bits of the value and put that in the left device, and then the second 2 bits and put that in the right device. Once we have answered all these 3 questions, we can accurately capture data value dependence. We answer the what, how, and where, then we know what values are stored in our devices, and we can capture the energy accurately. So we'll integrate that into our modeling framework. We have a data value dependent model with that red arrow on the left that goes into our data value calculation. This informs our component model library in order to get accurate energy estimations from this library, and then we get accurate energy estimations for our system. However, now we have another problem. There's a lot of values that we need to calculate. There's many weights, there's many inputs, there's many outputs, and in full deep neural networks, we might calculate billions or trillions of values. This can be slow, very slow. And prior works have not addressed the speed concern, which precludes doing effective design space exploration, where we need to evaluate many different design points. So to solve this issue, we'll look at distributions. The typical deep neural network layer will have actually pretty predictable distributions of your inputs, outputs, and weights. I have here a typical ResNet 18 layer where you have your weights as a normal-ish distribution, the one in green. Your outputs will be a normal-ish distribution. In this layer, it was more peaky than the weights, but similar, normal. You can get it with the standard deviation and mean value. And then finally, your inputs are a right skew distribution. And this is common across deep neural network layers in ResNet 18. It's found across many CNNs. It's found across different transformers and many different types of models. So this is something that we can reliably use to estimate energy. How do we actually plug this into our component model? So let's say we have to model many, many devices, and we need to calculate the energy for all of them in aggregate. We'll answer our 3 questions, this time for the distribution. First, what distribution are we processing? We'll say it's just a normal distribution between 0 and 15, centered about halfway through the range. Next, how does the system represent it? We'll bin our different values into buckets, and for each one, we will calculate the bit representation of the different values in the bucket. So here we have a distribution from binary zeros to binary all ones. Next, to where we map the bits of the distribution. So we'll take each of our bins in the distribution, we'll chop them up into 2-bit chunks, just like before, and now we have a different distribution. This one is the bits that are actually programmed into our devices. And finally, this is the value that's programmed into our devices. So we can just say The average conductance is the average value of the different weights that are programmed in. Now we can calculate the average energy, which lets us effectively model the energy of the system. Because when we're modeling the system, we don't care about the energy of a full device. We just want the whole system energy to be correct. So we'll calculate the average energy of the different devices, add them all up, and then get an accurate system energy. So to model data distribution dependence quickly, we need to answer the what, how, and where for distributions. Finally, the magic bullet of this is that it lets us do one calculation, the average, for any number of reads. So if you run a mobile net with a few 100,000 multiply accumulates, or the latest LLM with billions or trillions, you're still going to do one average. So regardless of how big your neural network is, our framework is still going to be fast to estimate the energy. So we integrate this into our modeling framework. We have this fast data distribution dependent model over on the left, and we inform our component library with that in order to get fast and accurate estimations of energy. Once we have this, that's the full CiMLoop. So we have our 3 challenges addressed. Now let's compare this to prior works. So our first comparison is what we do. We compare to 2 prior works that may model different design points in the compute memory space. The first one is NeuroSym, which models a memory macro. It is data value dependent, meaning it's accurate. It models every single value that propagates to this macro. However, it's very slow because it has to model a lot of different values. You can see that with this point on the very bottom left here. It's very slow on the model speed axis, but very low error on the model accuracy axis. Next, we have data value independent, or time loop. This one assumes an average energy that it does not calculate using the distributions. So it just uses a fixed energy per read and uses that for every single workload. You can see this has the 28% average error that we talked about earlier, but it's a lot faster. It's about 1,000 times faster than NeuroSym, the data value dependent. Next, if we add CiMLoop to the plot, we're over here on the top left. So we're fast, about 1,000 times faster than NeuroSym, the data value dependent, and we are high accuracy. So we're nearly the same energy error as NeuroSym, and significantly lower error relative to time. So same speed, 10x lower error than data value independent, and similar accuracy, but 1,000 times faster than data value dependent. So this framework is fast and accurate. Next, we validate the framework against real designs. So we use these 4 fabricated compute memory publications. Each of them have unique devices, circuits, architectures, tested workloads, and mappings. Now, I won't go too deeply into the validation because there is a lot of validation out there. If you're interested, I recommend you look at our published open source code, which has all of these and more. But we'll just give some high-level aggregates right now. So we report the CiMLoop average error over a few metrics that are commonly reported in different compute memory works. The first one is a supply voltage sweep, where they'll connect the macro to a different supply voltage, and they will change it and measure the energy and latency, or energy and throughput. So the next one is a bit precision sweep, where they will test different input, output, and weight precisions and see how that affects the energy and throughput. And finally, it's the per component breakdown, where they look at the different components and the energy and area of each one respectively. Over all of these, CiMLoop consistently gets relatively low error. It has at most 8% error, and on average, just 2 to 5% for most of these. Now, finally, we have a fast, accurate, and validated framework. Let's go back to our question from before. We have 3 different published macros, and we'd like to find which one has the most energy efficient architecture. Published results have a lot of different choices, so we can't compare them directly. If we did compare them directly, we could just look at the results from their papers. They report their energy efficiency in teraops per watt or petaops per watt. Doing this would be an apples to oranges comparison. It wouldn't be fair because it has all of these different factors. So looking at the values straight from the papers, we would get the misleading takeaway that architecture B has the best energy efficiency because on the plot, it has the highest power. However, we can do better with CiMLoop. So using CiMLoop for all architectures, we will use the same devices. We'll scale them to the 7 nanometer technology nodes. They have the same circuits. We use the same 8-bit ADCs, run the same workload, and set up the design to support 8-bit computations. So in order to compare even one level of the stack, notice how we had to touch every single one. When we do this, we get a much different result. And this is our apples to apples fair results, which has the accurate takeaway that the lowest energy choice is actually going to depend on your workload. If you have one input and wait bit over here on the left, you will have highest energy efficiency with architecture A. You have 4 input and wait bits, you'll have the highest energy efficiency with architecture B. And then with 8, you'll have the highest energy efficiency with D. So this is a very different result that we actually saw just reading the papers and taking their numbers. And that really speaks to how important it is to have a modeling framework that can take all of these factors into account when you're creating architectures and actually designing compute memory macros or making decisions at any level of space. So to review, CiMLoop introduces flexible models to support all different levels of the stack, from devices to circuits to architectures, workload and mapping. It includes accurate data distribution dependent energy modeling with 10x lower error than prior works, and fast statistical energy models that are 1,000 times faster than other accurate works. It's open sourced, it's out now, it's released. If you are interested, you can scan that QR code or just Google CiMLoop, it'll come up. It includes models of published works, full architectures, different devices that you can plug and play, many different deep neural networks or components too that you can swap all of them. And then finally, we've been looking at some even optical computing, where it's architectures that compute with light. So we have 2 designs that do that too, if you're interested in that as well. And so thank you for listening, and I would appreciate any questions.